There, this is the second video, and this is going to be questions 11 to 20. So this is question 11. Okay, which equation represents the second ionization energy of an element X? So if you lose 2 electrons, you are wrong. You only lose 1 electron per ionization energy. Okay, we're going to start off, if it's the second, we're going to start off with the X positive, and we're going to end up with X2 plus. So the answer must be B. Simple as that. Okay, because these show X2 minus. Ionization energies are all about losing electrons. Okay, if you gain electrons, that's something called electron affinity. So that's not this. So the answer is 11B. Let me stop now. Okay, these ones are a bit annoying. These can be quite confusing. Let's have a go. This is number 12. All right, so what have we got? We've got 2x's and 6h's. Oh, it's not so bad, actually. And we're making this, aren't we? So what are we making? Let's have a look. X, there's H, 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 and H, and H. So we're making these bonds, okay? And there's a mystery amount there, but we know how much they all add up to. So we're making, and this is how I do it. I always draw them so I can tick the bonds off. 1, 2, 3, 4, 5, 6. So we're 6 of these. 6 times 3, 9, 5. Okay. Plus, we're making an XX, aren't we? This one. Plus whatever XX is, I'm going to call that. All right, let's call that X. Okay. That plus that, okay, is going to give me minus 2775. Now, I just realized what I've done there. I think I'm confusing you. This is the bond energy, but we're going to say minus because we're not breaking the bonds, we're making the bonds. Okay, so there you go. So now if I do it like this, I'm going to say plus minus X as well. And if I do it like that, I should get the answer you'll see what I mean. You'll get the bond energy then. Okay. By the way, bond energies are all positive, so the answers can't be A or B. Okay, so let me get my calculator out. All right, so we got 395 times 6 is equal to that. So I get here minus 2370 plus X is equal to minus 2775. So now I'm going to put it on the other side, obviously. So I get 2775 minus, whoopsie daisy, minus 2775 plus 2370. And I get minus X is equal to minus 405. So the bond energy is 405. I hope that makes sense. So the answer is D there. Okay. If you've got any problems, give me a shout. I'll redo them. Okay, this one is one of these calorific ones. Okay, so we got 50 cc's of 2.5 molar HCl, and we add it to 50 cc's of 2.5 molar NaOH. So the same number of moles is being added to each other, which is good. Okay, so nothing is in excess. So here we go. Well, we know delta H is equal to mc delta T. Okay. Now, if we're going to make a delta H, this has to be minus. And we have to divide by the number of moles, and we divide by 1,000 to get the kilojoules. But I've just realized that the answer they want is in joules, so we don't have to do that. So here we go. Minus M is the volume. The volume of water. Now we're adding 50 there, and we're adding 50 there, so it's 100. So the answer isn't A or B, is it? So it's either C or D. So it's minus 100 times 4.2 times the difference, which is 17. So no difference yet here. So it's either C or D so far. Divided by the number of moles. Number of moles is equal to CV. C is 2.5 molar. V is, what's V? 50. 50 times 10 to the minus 3, isn't it? Yes. 50 times 10 to the minus 3 is 123. So 123, that's right. So it is, I'm looking for this number. This is 0.05, so the answer must be this one. Okay, because they haven't converted it to decimeters cubed there. So the answer must be C. All right, I hope that makes sense. Bye. And this is a nice easy one, which is only van der Waals are being overcome. Well, anything to do with ethanol has hydrogen bonding, so it's not that one. Anything to do with water has hydrogen bonding. If we melt solid carbon dioxide, we are breaking van der Waals. Now, it could have been butane, couldn't it? Because this involves van der Waals as well. But as you see, they're going from liquid to solid. So this one is overcoming van der Waals. So it must be C because we're overcoming them. In D, we're making them. Okay, so it can't be D. So the answer is C. This one looks relatively straightforward. Titanium occurs naturally as the mineral rutile, TiO2. One possible method for extraction is titanium is to reduce the rutile by heating with carbon. There you go. Standard enthalpy changes are for formation of that and that on that and that. What's the enthalpy change for the reaction? Right, this doesn't look too hard. Okay, so TiO2 plus 2 carbons gives Ti plus 2CO. We're going to use formation information. So down here, I'm going to write my elements, Ti plus O2 plus 2 carbons. And that changes a formation and that changes a formation. Obviously, we don't have to worry about the carbons because that's an element and standard enthalpy change of formation of an element is 0. And we don't have to worry about the titanium. So we want this delta H reaction. This is delta H1. This is delta H2. Delta H reaction is equal to, we go from here to here, which is minus delta H1. And we go from here to here, which is plus delta H2. Delta H2 is 2 carbon monoxides. And that is going to cost me 110. So that's minus 110. That's delta H2 minus delta H1. Delta H1 is the formation of a titanium oxide, which is minus 940. Minus 940. And what do we get? Here we go. Right, 2 times minus 110 is equal to that, plus, because there's a negative and a negative, so I get 720 and I get positive 720. All right, so that's the answer. C is the answer to that one. Whoops, these ones are quite straightforward. Which reaction has an enthalpy change equal to the standard enthalpy change of formation of propane? First of all, we have to know propane. Propane is a gas, okay? So could be that, could be that, could be that, not that, okay? Next, we have to know carbon is a solid. Not that, not that. It's got to be that one. So the answer is C. This is another bond energy one, isn't it? I think. Standard exchange, what's the bond energy for that? Oh, this should be okay. So what are we doing then? Let's draw this thing. N, F, F, F. And we're breaking how many? We're breaking 3 here, but we're breaking 6 in total, aren't we? So we're breaking 6 bonds. Okay. And breaking 6 bonds apparently costs me 1668. So if I break 1 bond, it should be 1668 divided by 6. And I get 278. Now, a good thing to know where you are here, bond energy, they're never negative, are they? So it can never be A or B. So it's got to be C or D, and the answer is C. Okay. Okay, this one is a bit of a challenging one. Hess's law can be used to calculate the average CH bond energy in methane. We're given atomization, formation, and combustion data there. Okay, and which one of these do we need to perform the calculation? Well, first of all, let's have a look at what we need. We're going to start off with methane, which is a gas, and we're going to form carbon gas plus, oops, not 2. 4 hydrogens gas. Okay. Now, I've got to form some sort of Hess's triangle here, and I'm going to start down here with the elements in their standard state. Carbon solid plus hydrogen gas. Okay, so if I go from here to here, what's that? Well, this is the formation of methane, which I need in my Hess's law anyway. So formation of methane. So it could be A, because there it is. Could be C, and it could be. Oh no, I don't think we can do it. We can't do it with that. All right, you'll see in a minute. So it could be A or C. Now we need this branch of my triangle, and so carbon solid to carbon gas is the atomization of carbon, isn't it? So this is at of carbon. All right, and we also need the atomization of hydrogen to get this. So this is the atomization of hydrogen. Okay, so which is that? Carbon, what's this formation? Atomization, so the answer is A. All right, that's a bit of a tricky one, I guess. Okay, as you know, we don't have to learn these 1, 2, 3 things anymore, but they're really good questions, so that's why I put it in. We'll be seeing a lot more of these. Okay, which the labels represent? W, where's W there, is delta H of the forward reaction. Well, it's not, is it? Delta H of the forward reaction is that. So number one can't be right. Not even going to read this last bit because it's wrong, isn't it? Z is the delta H of the back reaction. Yeah, it is. There's the products, there's the reactants, and there's it. That is delta H, so that's good. Y is the activation energy of the back reaction. Yes, it is. From there to there, to the top of that, from here. So that's good. So number 2 is good. Number 1 is rubbish. Number 3 here, X is the delta H of the forward reaction. Yeah, it is. From reactants to products. There you go. So that's good. And W is the activation energy of the forward reaction. Can't see. Yes, it is. That's right. So the answer is 2 and 3 are correct. So that gives us a C. Okay, one more to do. This is the last one. Let's hope we get this one right. These are relatively straightforward. Okay, well, I think so. Let's go. Right, so we've got an energy cycle here. We've got to create a Hess's thing, haven't we? So down here, we've been given formation data. So I'm going to have to write 2H2 there, plus 2O2 there, and put arrows up here. Okay, so the one I want is delta HR. I'm going to define that as delta H1, delta H2, delta HR equals minus delta H1 plus delta H2. Delta H2 is the formation of 2 waters. Okay, 2 waters. 1 water costs me 285, so that's minus 285.8 apparently. Okay, now oxygen, we don't have to do anything because it goes from oxygen to oxygen, so we can relax about that one because it's going to be 0, isn't it? So that's delta H2 minus delta H1. Delta H1 is the formation of 2 hydrogen peroxides. That's minus 187.8. Let's figure all this rubbish out. Okay, I don't know what the answer is. So let's have a look. 2 times minus 285.8 is equal to that. And we're going to add, 2 times 187.8. And we get minus 196. Okay, so that's the answer to that one. All right, that's number 20, and we're done. I'll post this now.